Hi guys, welcome to chapter 13. We're going to talk about work and power and machines and all kinds of stuff like that in this chapter. We're going to cover section A today, okay? So let's talk about what is work. You might think you're doing work, but when it comes to physics, there's some requirements for work to be actually, considered. Work is actually done anytime a force causes an object to move. Okay, that's the first thing. So if you're pushing on an immovable object, you're absolutely exerting a force to it. But if the object isn't moving, you're not doing any work. Okay. But the movement of the object has to be parallel to the force as well. So if I'm carrying a heavy object and I'm walking with it, I'm lifting up, I'm exerting an upward force on that object, but the movement of the object is not parallel to that force. So that's not even considered work. It's heavy, it is tiring, but scientifically speaking, it's not considered work. Work is a scalar measurement, meaning that the direction doesn't matter. The direction of the force and the movement have to be parallel, but it doesn't matter if it's left, right, up, down, east, west, whatever. So we don't include that in the measurement. Real quick, this little table here, let me move myself out of the way, shows us some different scenarios and asks the question of whether work is being done or not. Okay, so if I push on this box in that direction and the box moves in that direction, then yes, absolutely work is being done. Okay, if I am simply walking, okay, I'm holding myself up away from gravity, but I'm moving forward, that's no work. If I lift up a heavy object off the ground, simply while it's moving up off the ground, the force is opposite of gravity, away from gravity. The object's moving in the parallel direction, so yes, work would be done, okay? And again, I already told you this scenario. If I'm carrying that object, now that object is moving in that direction, even though I'm applying this kind of force to it. Not parallel, so that's not considered work, okay? We do have some calculations for work. Work is equal to the force times the distance. So the force that you're applying times the distance that it moves is equal to work. Okay, force is in newtons, and then distance is usually in meters. If it's not, it should be converted because our unit for work is newtons times meters, which is called a joule, and it's named after a scientist. Okay, so the unit for work is joules, right? Let's look at a calculation. So look at, let's see, where are we at here? Page 297, example 13-1, okay? So how much work does a ship lift? A ship lift is something that lifts ships, in like a Panama Canal kind of situation. Anyway, how much does a ship lift do? How much work does a ship lift do if it applies 13,230,000 newtons to lift a ship 73.15 meters, okay? So we know our force, that's the 13 million. We know our distance, that's the 73 meters. And we know our formula. So we multiply those two things together, and that gives us 967,800,000 joules, okay? Work is equal to that many joules. Now in science, we don't like really big numbers, we don't like really small numbers. That's why we use the metric system, okay? So we could also refer to this as kilojoules. We would move that decimal place 3 times to the left, just like 1 meter is 1,000 meters is equal to 1 kilometer because we can move that decimal place. We can shorten the unit there, or we can do it again. We can move it another 3 times and use another prefix, mega. This would be 967.8 megajoules. Okay. You know these prefixes from computers. We talk about kilobytes, we talk about megabytes, we talk about gigabytes, which is the next 3 over, and we even talk about terabytes, which is the next 3 decimal places over, okay? But that's a different conversation. All right, now let's talk about power. Power is the rate of doing work. It's measured in watts. Okay, so this W, I don't like the confusion. They use the W for work, but the label for power is watts, okay, also named after a scientist. It's another scalar measurement, so the direction doesn't matter. So I want you to look at this scenario right here. We've got this horse pulling this little plow kind of thing on a field. If that horse exerts a certain amount of force and it moves that plow a certain amount of distance, that's how much work it's doing. If I hook up a tractor to that little plow or a quad or something, and it exerts the same force and moves the same distance, the work between those things is going to be absolutely the same. The horse and the tractor are going to do the same amount of work. But there's an obvious difference there, and that's power, because the time is going to be different. The tractor is going to be able to do this much more quickly, okay? So in order to calculate power, we divide work by time. So we still calculate the work that's being done. If it's the same for both the tractor and the horse, it's going to be faster with the tractor. And so we're going to wind up with a larger quantity, a bigger number of power, okay? And again, work is still in joules. Time has to be in seconds for this, okay? Let's look at an example. So now we're on page 298 in your books, okay? It says if a Model T engine can do 13,428 joules of work in 15 minutes, how much power does this produce, okay? So we know our work, that's the 13 million joules. We know our time, it's in 15 minutes, but it needs to be in seconds. To use the unit of watts, it needs to be converted to seconds. So I just convert it to 2 seconds. 15 minutes times 60 is 90 seconds, okay? Power is equal to work divided by time. So 13,428,000 divided by 900 gives me 15,000 watts, okay? We could shorten this. We can do the same trick and turn that into 15 kilowatts, okay? That's power. Fun fact, by the way, let me go back here. This would be considered 1 horsepower. That's what the horsepower, we talk about horsepower with engines. It's actually an old measurement based on how much a horse can pull. So that plow would be pulled with 1 horsepower. If I hooked up a tractor to it, it would be pulled with additional horsepower, okay? Crazy, right? All right, we did this. Okay, now let's talk about machines. Machines make our lives easier, but we're not talking about like complicated machines yet. We're really going to only talk about very basic, non-moving, well, somewhat moving, but very basic parts here. And these are devices that make work easier, okay? In the next couple of sections, we're going to talk about these 6 main type of simple machines. And what they do is they change the magnitude, so the amount, or the direction, or the distance that the force travels while you're doing work, okay? And I'll talk about that more as we actually break down these different simple machines. But we're going to talk about an inclined plane, a wedge, a screw, a wheel and axle, lever, and pulleys. Those are our 6 simple machines, okay? Part of how they make things easier is by changing the mechanical advantage, all right? So the mechanical advantage it's the advantage that the machines give us with the work, okay? And it can do it in 3 ways. It can multiply the effort or the input force. It can multiply the input distance. It can increase the distance, or it can just change the direction, okay? These are a little complicated. We'll spend much more time on these in class, so hopefully you don't miss that lecture, okay? We also will talk about the difference between the ideal mechanical advantage versus actual mechanical advantage. So ideal is if there's no loss of work to friction. If you're just, everything's working perfectly, the input will always equal the output, okay? The machine does the same amount of work that the person does. But in all actuality, we lose some, okay? So if I'm pushing a box up a ramp, there's friction. So my output is going to be less than my input. I'm going to lose some of that work to friction, and that's known as the actual mechanical advantage. We probably won't do any calculations on this, so don't freak out. There are a lot, okay? And the last kind of definition that goes along with mechanical advantages is efficiency. Since there's a difference between the perfectly working machine with no friction and an actual machine, we talk about how efficient a machine is. The higher the efficiency, the closer to 100 a machine is, the closer it actually is to this ideal mechanical advantage. And it's just a ratio. It's a comparison of the actual mechanical advantage to the ideal mechanical advantage, okay? And we convert that into a percentage. So if a machine has an efficiency of 40%, that's losing 60% of its work. You want the efficiency to be as close to 100% as possible, okay? All right, got a little problem for you to work on. This is about work, okay? So think back to work. Remember, work is force times distance, okay? So you need to carry 5 cans of paint upstairs. Would you do more work carrying them one at a time or all at once? Okay, I want you to pause the video and really think about this for a while, okay? All right, you're back. Let's talk about it. So I'm going to apply random numbers to this. I'm going to say that each paint can has a weight of 1 Newton, okay? Because that's the force required to lift it up off the ground. Okay, remember, weight is the measurement of gravity. So it takes 1 Newton to lift a paint can, okay? I'm going to say that the upstairs is a distance of 10 meters, okay? So my force is 1 per paint can, and my distance is 10 meters, okay? So if I carry 1 can at a time, I'm going to have 1 Newton times 10 meters, which gives me 10 joules. But there's 5 paint cans, so I have to do that 5 times for a total of 50 joules, okay? Or I can pick up all 5 cans at once, okay? I can carry all 5 cans. Each can is still 1 Newton. If I do it all at once, I'm going to be carrying a total of 5 Newtons. And I'm going to still go up a distance of 10 meters, but I only have to do it once this time. That gives me 50 joules. Look at that. They are exactly the same. So you do the same amount of work whether you carry the cans all at once or one at a time. It's up to you which you think is harder, but the work is the same. All right? That's it. See you later.